So we've seen the list of decompositions that require a lot of heat. And of course, lots of compounds decompose. Those were just 3 special classes. But the ones we're about to do, I would say, are truly special. They're what we call spontaneous decomposers. So spontaneous decomposers, to be spontaneous means to do something, without warning, to do it in a surprising way. And in the case of chemistry, what it means is it doesn't even require heat. Like, for example, if you had a white powder, this calcium chloride, and it was a spontaneous decomposer, the spontaneous decomposer would just simply opening the top, the white powder would start spewing out gases. Calcium chloride is not a spontaneous decomposer though, so this isn't a really good example. And if you stop and think about it even for a second, I can't have a chemical bottle of a spontaneous decomposer because it would just decompose sitting on the shelf. That would be ridiculous, right? So spontaneous decomposers, you can never buy a bottle of these things. So in this lesson, what we're going to figure out is, well, how do we make spontaneous decomposers if you can't actually buy them? Okay? All right, so these are ones that don't require heat. And the answer is they get made as you go through the reaction. They're always products of double displacement reactions. And so you don't buy a bottle of them, you make them as you go. Let's look at an example. This one you for sure have seen. This one is the one where every time you go to some elementary or middle school science fair and somebody does the volcano, right? Usually you're using like a little acid like vinegar, a little baking soda, which is a carbonate. Here I'm doing my acid as HCl and I'm using sodium carbonate, but it's the same idea, right? So if we wanted to find out what's the spontaneous decomposer, well, neither one of these are spontaneous decomposers because I can buy a bottle of that and I can buy a bottle of that. Quite often, it depends on how you do it. It works just fine to start with a solid sodium carbonate, but you could actually start with it dissolved in solution too. You know what? Let's start with it dissolved in solution. So I want you to picture this as a powder in solution. And acids are always aqueous. They're always dissolved in water, right? So they're always aqueous. No problem at all. That might be an important note. Acids are always aqueous. That is terrible, terrible, terrible writing. But you should get that in your notes. Ionic compounds, right? This is ionic. It depends on if it's in water or not. But this time I'm going to say it's aqueous because we are not going to add any heat here. No triangle whatsoever. You don't have to. You're just going to pour these two together. So imagine yourself with a beaker of sodium carbonate and a beaker of HCl. Pour them together. And what will happen is you will immediately see a foaming over volcano of this stuff because when they do the double displacement reaction, you get sodium chloride, right? That goes with that. And you get a little bit of H going with CO3. With both of these, I need to check charges. +1, -1, good to go. +1, -2, I need a little 2 down there. And if I were to check solubility rules, that has a 1A element in it, so it's aqueous. This has a 1A element in it, and it's an acid, so it's aqueous, remember, because all acids are aqueous. And you look at this and you think, wait a minute, nothing is going to happen in this reaction. If they're all aqueous, if I were to go down to my total ionic equation, then they would all dissociate, and they would be full of spectator ions, and there would be no net ionic equation. But that's not what happens here. And remember, AP will never give you a reaction that nothing happens. So something does happen here. And it's not that we misread our solubility rules. What happened here is this compound right here is what I call a red flag compound. See, I'm going to put a little red flag on it. This is Jones terminology. The AP doesn't use this. I call these red flag compounds because they're ones you got to spot. Every time you finish a double displacement reaction, you need to look and see, is there a spontaneous decomposer? And there is. This spontaneous decomposer will decompose into water and CO2 gas. That's a gas. Water, as you know, is a liquid, especially if you don't have any heat. So those two are the decomposition products of H2CO3. And you might wonder, how fast does that happen? It's instantaneous. You've seen the volcano. It foams over immediately. The reason it foams over is because of all the CO2 gas that's trying to escape. So that's our first example of a spontaneous decomposer. Any guess how many spontaneous decomposers there are in the world? 3 total. And that's the first one. So H2CO3. All right, let's do the total ionic equation though, because we're going to have you do this in practice in just a little bit. This was aqueous because I said it was dissolved in water. It was a solution, right? The word solution always means dissolved in water. So I'm going to dissociate those ions. I am going to put charges because remember we are not saying that that is sodium metal. Those two dissociated. Sodium plus dissociated because that was aqueous, and chloride minus dissociated. And then of course this decomposed into H2O and water. And these do not dissociate any further because that's covalent. That's covalent. There's no metal and nonmetals. They can't do that. So that's a liquid, that's CO2, they stay as they are. Now if we hunt for spectator ions, I think chloride looks like it didn't do anything, didn't change its charge. Sodium looks like it didn't do anything, and we end up with CO3, 2 minus, reacting with H plus, in other words carbonate, found some acid, and made a little bit of liquid water, and that CO2 that foamed over the volcano so quickly and so instantly. Notice, no heat required. Because these are spontaneous decomposers, they do not require heat. They are always the products of double displacement reactions. I noticed in the last video I didn't balance my reactions. Let's do it here. H2, so we need a 2 there. I got 1 carbon, 1 carbon. We've got 2 plus 1 is 3 oxygens. We have 3 oxygens. We're good to go. So the process of writing the net ionic equation is the same. Your job is going to be to spot these red flag compounds. So let's make sure that you know what those 3 red flag compounds are. And let me get my red pen out, because every single time you see one of these made, like we just saw this one made, as a product of a double displacement, you should exclaim in your head, red flag, red flag, red flag, because you have spotted something most people won't, and then decompose it. Or you could say, because you know when they decompose, like this one makes water, liquid water, and CO2 gas, they all make gases. That's why we're studying these in the gas law unit, right? Is they all make gases. So since they're all going to make gases, if you spot one of these red flag compounds, you could stand up and exclaim, I have gas. Yeah, do that in your house. Okay? This one, I don't need to put state symbols on these, by the way, because they don't exist, right? They fall apart. This one, sulfurous acid. Let's get names down. This is carbonic acid. Carbonic acid. This is sulfurous acid. This one's probably the trickiest one of all because you know H2SO4 is a very common strong acid, but it does not decompose. Sulfurous acid does, and it decomposes into, any guess? Any guess? Any guess? SO2. How do I know? Well, CO3 became CO2. SO3 logically should become SO2, I think. Makes sense, right? And this one, of course, is just its standard name. It is ammonium hydroxide. It is a spontaneous decomposer. It is what Windex is. You notice how Windex, you leave Windex sitting out and you get, oh, I wish I'd written the water over there. I mean, it doesn't matter. But the water is, of course, liquid. But the ammonia, this is a very important chemical. Ammonia is in Windex. When you open it, the ammonium hydroxide decomposes and lets a little ammonia out. In CP, I generally do this one in class, and I would if we were in class. I don't typically do this one because SO2 it's stinky. It's the smell of a skunk. And I don't typically do that one. It's not quite so bad. Matter of fact, when we get back into class, we will do a reaction that makes one of these. I'm sure it will show up, for sure. Okay, so those are the 3 spontaneous decomposers. Now your job in the assignment that's to follow is to hunt for these red flag compounds and decompose them. And in all double displacements from here on out, if you ever assign your solubility rules and everything's aqueous, you got to go, ha, they're trying to trick me. There's a spontaneous decomposer here. There's a red flag here, and decompose it. Okay? All right, so now that you have the notes on this, the assignment will have a whole bunch of double displacement reactions that produce spontaneous decomposers, and your job is to write the total and net ionic equation of each one as practice. All right, go to it.